Imagine waking up to headlines that sound impossible. The Mississippi River has stopped moving, not slowed by drought, not blocked by ice, completely still. At first, most people would assume it was a mistake, a temporary anomaly, or perhaps an exaggerated news report. After all, rivers do not simply stop, especially not one that has been flowing across the heart of North America for millions of years. But within hours, scientists would realize something far more disturbing. This is no ordinary environmental event. The single most important river system in the United States has suddenly become motionless, and almost every major industry, ecosystem, and city connected to it is about to face a chain reaction unlike anything in modern history. The Mississippi is often described as America's backbone, stretching more than 2,300 miles from northern Minnesota to the Gulf of Mexico. It drains water from 31 U.S. states and 2 Canadian provinces. Nearly 40% of the continental United States eventually sends rainwater into this single river system. Every second, enormous volumes of freshwater travel south, carrying sediment, nutrients, wildlife, commercial cargo, and the lifeblood of entire communities. The river is so large that from space, its muddy water can be seen pushing deep into the Gulf of Mexico. Now imagine all of that movement ending in a single moment. At first glance, the river itself would look strangely peaceful. Boats tied to docks would barely drift. Floating debris would remain almost frozen in place. People living near the banks might even describe the water as beautiful. But underneath that calm surface, one of the largest natural transportation systems on Earth would already be collapsing. More than 500 million tons of cargo travel along the Mississippi River every year. Grain harvested from the Midwest, coal, fertilizer, petroleum products, chemicals, steel, and construction materials all depend on barges moving through this massive inland highway. Unlike trucks or trains, barges can carry enormous loads at relatively low cost. A single towboat pushing 15 barges can move as much cargo as over 1,000 semi-trucks. The moment the river stops flowing, navigation becomes unpredictable. River currents are carefully studied because they help vessels maneuver through bends, channels, and locks. Without current, sediment begins settling in unexpected places. Navigation markers lose much of their meaning. Sandbars slowly emerge where none existed before. Barges scheduled to deliver grain to export terminals begin falling behind schedule within the first day. Shipping companies immediately halt departures while engineers try to understand what has happened. Across the Midwest, farmers preparing shipments barely notice the danger at first. Their grain elevators remain full, waiting for barges that never arrive. Within days, storage facilities begin reaching capacity. Harvest schedules are disrupted. Railroads suddenly receive emergency requests far beyond what they were designed to handle. Highways experience growing congestion as thousands of additional trucks attempt to replace just a fraction of the river's shipping capacity. Meanwhile, another crisis is quietly beginning beneath the surface. Hundreds of cities draw drinking water directly from the Mississippi River. Massive treatment plants continuously pump river water into systems serving millions of homes, hospitals, schools, and businesses. These facilities were designed around a living river with constant movement. Flowing water naturally dilutes contaminants, replaces withdrawn supplies, and helps maintain water quality. A motionless river changes every assumption those systems were built upon. Engineers monitoring intake stations begin noticing something unusual. Water near pumping facilities is no longer refreshing itself. Small concentrations of pollutants that would normally drift downstream remain trapped near municipal intakes. Industrial discharge, agricultural runoff, and untreated stormwater begin lingering instead of dispersing. Treatment plants work harder to maintain safe drinking water, consuming more chemicals and energy with every passing hour. Then scientists make a discovery that sends emergency agencies into crisis mode. The Mississippi is not merely carrying water to the Gulf, it is constantly pushing back against another powerful force. Without that steady downstream pressure, something invisible begins moving inland. Salt water from the Gulf of Mexico starts advancing north through the river channel, mile after mile, threatening freshwater supplies that millions of people depend on. And once that process begins, stopping it may prove far more difficult than anyone imagined. What makes this threat even more dangerous is that it would not remain confined to the Gulf Coast. The advancing saltwater wedge would slowly travel upstream beneath the surface, often invisible to the naked eye. Freshwater floats above denser seawater for a time, but pumping systems eventually begin drawing increasingly salty water into treatment plants. Cities such as New Orleans have already experienced temporary saltwater intrusion during periods of unusually low river flow. In this scenario, however, there is no flow left to resist the ocean at all. Engineers would scramble to build emergency underwater barriers, extend water intake pipes farther upstream, and transport drinking water by rail and truck. These measures might buy valuable time, but they cannot permanently replace a river that is no longer doing the job nature designed it to perform. As officials struggle to secure drinking water, another problem emerges hundreds of miles inland. The Mississippi River is not an isolated channel. It is connected to an immense network of tributaries, wetlands, oxbow lakes, floodplains, and underground aquifers. Countless smaller rivers depend on the Mississippi's movement to regulate their own water levels. When the main artery suddenly becomes still, the balance throughout the watershed begins changing in unexpected ways. Some tributaries would initially continue flowing, but instead of feeding into a moving river, they would empty into stagnant water. Their currents would weaken near the junctions, allowing mud and sediment to accumulate much faster than normal. Natural drainage slows. Low-lying farmland remains waterlogged after storms because runoff no longer exits efficiently. Elsewhere, certain channels become unusually shallow as incoming sediment settles instead of being carried downstream. Engineers responsible for levees, dams, and navigation locks suddenly face conditions that none of their models were designed to predict. Wildlife feels the effects almost immediately. More than 260 species of fish inhabit the Mississippi River basin. Many depend on seasonal currents to migrate, reproduce, locate food, or transport eggs and larvae. Some species instinctively swim against the current during spawning seasons. If the current disappears overnight, those biological signals vanish with it. Fish gather in unusual concentrations, become trapped in isolated sections, or fail to reach traditional breeding grounds. Commercial fisheries begin reporting dramatic declines within weeks. Birds are affected as well. Every year, roughly 60% of North America's migratory birds use the Mississippi Flyway, one of the world's greatest migration corridors. Wetlands along the river provide essential resting and feeding habitat during journeys that span thousands of miles. As water quality deteriorates and marshes begin changing, insects decline, aquatic vegetation dies back, and food sources become increasingly scarce. The disruption extends far beyond the riverbanks, reaching forests, grasslands, and coastal ecosystems across an entire continent. Yet perhaps the greatest environmental consequence would not become obvious until months later. For thousands of years, the Mississippi has been carrying enormous amounts of sediment southward. Every year, it delivers millions of tons of sand, silt, and organic material into Louisiana's coastal wetlands. This constant supply has built much of the state's coastline, creating marshes that protect inland communities from hurricanes and storm surges. Without fresh sediment arriving, the coastline would begin losing ground at an even faster pace. Louisiana is already experiencing one of the highest rates of coastal land loss anywhere on Earth. Entire marshes have disappeared over recent decades because sediment delivery has been reduced by levees and river engineering. If the Mississippi stopped flowing completely, that remaining supply would fall to zero. Wetlands that serve as natural storm barriers would steadily erode away. Saltwater would penetrate farther inland. Coastal forests would die. Entire habitats supporting shrimp, oysters, crabs, and countless bird species would begin transforming into open water. Then comes the realization that changes at the mouth of the river are only the beginning. Far upstream, thousands of bridges, pipelines, power plants, factories, and cities were all built on one assumption that had never been questioned: that the Mississippi River would always keep moving. And once that assumption disappears, every piece of infrastructure along its banks must be re-examined, and some of the most unexpected failures have yet to reveal themselves. Long before anyone notices collapsing ecosystems or rising food prices, another hidden system begins to fail. The Mississippi River is deeply woven into America's energy infrastructure. Along its banks stand more than 100 major industrial facilities, including oil refineries, chemical plants, power stations, grain processors, and manufacturing complexes. Many of them were built beside the river for one simple reason: flowing water is essential. It provides transportation, cooling, industrial processing, and a reliable source of freshwater that cannot easily be replaced. The first warning signs appear inside control rooms rather than on the river itself. Operators monitoring intake pumps notice falling efficiency as stagnant water carries increasing amounts of algae, suspended organic matter, and concentrated pollutants. Cooling systems designed to circulate millions of gallons every day begin operating under conditions they were never engineered to handle. Some facilities reduce production voluntarily to avoid damaging critical equipment. Others are forced into emergency shutdowns after water quality falls below operational safety standards. Nowhere would the consequences be more serious than along the lower Mississippi corridor between Baton Rouge and New Orleans. This stretch of river contains one of the highest concentrations of petrochemical facilities anywhere in the world. Refineries here process enormous quantities of crude oil into gasoline, diesel, jet fuel, and countless chemical products used in plastics, pharmaceuticals, fertilizers, and consumer goods. Even a temporary disruption along this industrial corridor would ripple through national supply chains. Within days, fuel distributors begin reporting delays. Pipelines that normally receive refined products from Gulf Coast refineries experience declining throughput. Wholesale fuel prices climb as traders anticipate shortages. Airlines adjust fuel purchasing strategies. Trucking companies add emergency surcharges. None of these changes are caused by a lack of crude oil. They happen because one river has stopped supporting the industries built around it. But transportation and manufacturing are only part of the picture. The Mississippi River also plays a surprisingly important role in keeping electricity flowing across large parts of the country. Several power plants withdraw river water to cool turbines and generators before returning warmer water downstream. Without continuous movement, discharged heat accumulates near intake locations instead of dispersing. Water temperatures gradually rise, reducing cooling efficiency and forcing operators to decrease electrical output during periods of highest demand. That timing could hardly be worse. During a summer heat wave, millions of homes rely on air conditioning simultaneously. Electricity demand reaches seasonal peaks exactly when some generating stations may be producing less power. Grid operators begin shifting loads between regions to prevent blackouts. Emergency reserves are activated. Utilities ask consumers to reduce electricity use during afternoon hours. Most people assume the requests are related to extreme weather, unaware that the true cause began hundreds of miles away in a river that no longer moves. Then, another industry quietly enters crisis. Agriculture across the Midwest depends on far more than river transportation. Fertilizer production, irrigation systems, food processing plants, and export logistics all form a tightly connected network centered around the Mississippi Basin. As transportation slows, fertilizer deliveries arrive late for planting seasons. Farmers face rising costs for fuel and equipment. Grain prices increase, followed by livestock feed, meat, dairy products, and eventually grocery bills nationwide. Economists begin comparing the disruption to the supply chain crises that followed global pandemics. Except this time, there is no obvious endpoint. Every forecast depends on one unanswered question. Will the river ever begin flowing again? As uncertainty grows, financial markets react with increasing volatility. Insurance companies reassess billions of dollars in infrastructure exposure. Real estate values along vulnerable sections of the river begin shifting dramatically. Some properties lose value because water systems have become unreliable. Others unexpectedly increase as businesses search for locations connected to alternative transportation networks. Yet all of these economic shocks remain secondary to a much larger threat that few people initially recognize. For generations, Americans have viewed the Mississippi primarily as a river. In reality, it is also an enormous geological machine, constantly reshaping the landscape beneath its own waters. Once that machine stops operating, forces that have remained balanced for thousands of years begin changing direction. And what happens next has the potential to permanently alter the map of the United States itself. The Mississippi has never been a fixed feature on the American landscape. Over thousands of years, it has repeatedly abandoned old channels, carved entirely new ones, and shifted its course across vast sections of the continent. Geologists studying ancient river deposits have found evidence that the lower Mississippi has changed direction many times in the distant past. Entire valleys that are now quiet farmland were once occupied by the main river itself. Under natural conditions, the Mississippi is always searching for a steeper and more efficient path to the Gulf of Mexico. That process has not stopped. In fact, engineers have spent decades preventing one of the most dramatic river changes ever recorded. About 300 miles north of New Orleans, near a place known as the Old River Control Structure, the Mississippi comes dangerously close to the Atchafalaya River. Left completely alone, many scientists believe the Mississippi would eventually divert most of its water into the Atchafalaya Basin because that route provides a shorter, steeper path to the Gulf. Since the 1960s, one of the most complex river engineering systems in the world has carefully regulated this balance, allowing roughly 30% of the flow into the Atchafalaya while keeping 70% in the traditional Mississippi Channel. But imagine trying to regulate a river that no longer flows. The gates, control structures, spillways, and navigation locks that have shaped the lower river for generations suddenly lose the very force they were designed to manage. Instead of controlling moving water, operators are left overseeing enormous concrete structures connected to stagnant channels. Sediment settles around gates. Mechanical systems designed for constant hydraulic pressure begin functioning under completely unfamiliar conditions. Engineers quickly discover that maintaining infrastructure without river movement is almost as difficult as controlling floods. Meanwhile, the riverbed itself begins changing. Most people think of a riverbed as solid ground, but the bottom of the Mississippi is constantly reshaped by moving water. Sand dunes several feet high slowly migrate downstream beneath the surface. Channels deepen in some places while becoming shallower in others. Once the current disappears, this continuous remodeling comes to an abrupt halt. Fine sediment falls rapidly out of suspension, coating navigation channels with thick layers of mud. In certain locations, decades of accumulated deposits begin filling deep sections of the river much faster than expected. The consequences extend to thousands of bridges. Nearly 200 major highway and railroad bridges cross the Mississippi. Their foundations were carefully designed using decades of data about flowing water, erosion patterns, sediment transport, and seasonal river levels. When those conditions suddenly disappear, engineers must inspect every structure for new risks. Some bridge piers may become surrounded by unexpected sediment buildup. Others could experience unusual pressure changes as groundwater beneath the riverbed adjusts to an entirely different hydraulic system. None of these changes necessarily cause immediate collapse, but together they create enormous uncertainty for transportation networks carrying millions of people every year. Then, another unexpected problem emerges from beneath the ground. The Mississippi River does more than transport surface water. Its constant movement influences groundwater levels across broad sections of the surrounding landscape. Aquifers near the river exchange water continuously through porous layers of sand and gravel. Farmers, industries, and municipalities rely on these underground reserves every day. When the river stops moving, groundwater gradients begin shifting. In some regions, wells produce less water than expected. Elsewhere, stagnant river water slowly seeps into underground systems, carrying higher concentrations of contaminants than before. Hydrologists begin recording changes that spread far beyond the visible shoreline. Wetlands that once received seasonal flooding start drying in unusual patterns. Other low-lying areas remain flooded because natural drainage has weakened. Forests adapted to centuries of predictable water cycles begin showing signs of stress. Some tree species experience root damage after prolonged flooding, while others struggle as groundwater retreats below normal levels. The transformation unfolds gradually enough that many people fail to notice it at first, yet satellite imagery reveals an unmistakable shift spreading across one of North America's largest watersheds. And then, scientists begin asking an even more unsettling question. If the Mississippi has truly stopped flowing, what force powerful enough to halt one of the world's greatest rivers could also be affecting other freshwater systems across the continent? That possibility would trigger investigations reaching far beyond the river itself, opening a chapter far more alarming than the economic and environmental damage already unfolding. If the Mississippi River remained motionless for months instead of days, the crisis would begin entering a stage that no modern society has ever experienced. Emergency measures that initially seemed temporary would slowly become permanent. Water deliveries by truck could support individual towns for a while, but not major metropolitan areas. Alternate shipping routes might compensate for a small percentage of lost river traffic, yet they could never replace one of the busiest inland transportation systems on Earth. At this point, the country would stop asking how to survive the emergency. The question would become whether the nation could adapt to an entirely different geography. One of the first major transformations would occur inside America's farming belt. The Mississippi Basin contains some of the most productive agricultural land on the planet. Corn, soybeans, wheat, cotton, rice, and countless other crops benefit from fertile soils created by thousands of years of river flooding and sediment deposition. Although modern levees have reduced natural flooding in many places, the river still plays a critical role in maintaining regional water cycles. Moisture evaporating from the river contributes to local humidity, influences weather patterns, and helps sustain nearby ecosystems during dry periods. As the stagnant river begins warming under the summer sun, evaporation behaves differently. Water quality declines, algae blooms expand across quiet sections of the channel, and oxygen levels fall dramatically. Fish kills become increasingly common as dissolved oxygen drops below the levels needed to support aquatic life. Residents living near the river begin noticing foul odors spreading across nearby communities. Mosquito populations explode in stagnant backwaters, creating ideal breeding conditions across areas that once experienced constant water movement. Public health officials face challenges they rarely associated with the Mississippi. Warm, stagnant freshwater provides favorable conditions for bacteria and harmful microorganisms that normally struggle against continuous flow. Waterborne diseases become a growing concern in communities relying on untreated private wells near contaminated sections of the river. Recreational activities disappear almost entirely. Marinas close. Beaches along riverbanks are abandoned. Tourism that once depended on sightseeing cruises, fishing, and waterfront festivals quietly collapses. But even these problems remain local compared to what begins unfolding across the global economy. The United States exports enormous quantities of agricultural products through terminals located near the mouth of the Mississippi. Grain harvested throughout the Midwest is transported by barge before being loaded onto ocean-going ships bound for markets across Europe, Asia, Africa, and South America. As exports decline, international buyers begin seeking more reliable suppliers. Countries such as Brazil, Argentina, Canada, and Australia rapidly expand market share while American exporters struggle to move products efficiently. The consequences extend far beyond agriculture. Global commodity markets respond immediately to uncertainty surrounding one of the world's largest food-producing regions. Prices fluctuate sharply as traders anticipate shortages. Nations heavily dependent on imported grain begin increasing strategic reserves. Governments negotiate emergency supply agreements. Some developing countries face rising food costs that place additional pressure on already vulnerable populations. A river located entirely within the United States suddenly becomes an international economic concern affecting millions of people who have never seen it. Then another unexpected consequence emerges from space. Earth-observing satellites continuously monitor rivers around the world. Scientists studying climate, vegetation, groundwater, and land use would quickly notice that the Mississippi Basin no longer behaves like any other major watershed on the planet. Thermal images reveal rising surface temperatures along stagnant water. Radar measurements detect changing wetland boundaries. Ocean monitoring satellites observe a shrinking freshwater plume extending into the Gulf of Mexico. That plume has always played a critical ecological role. Freshwater flowing from the Mississippi influences ocean salinity, nutrient distribution, plankton growth, and marine food webs across large portions of the northern Gulf. Without continuous river discharge, coastal ecosystems begin reorganizing. Species adapted to brackish conditions retreat or disappear. Saltwater penetrates farther inland. Commercial fisheries targeting shrimp, oysters, and certain finfish face steadily declining harvests as nursery habitats change beyond recognition. And just as scientists begin mapping these environmental transformations, another realization begins spreading through research institutions worldwide. Every climate model, flood forecast, agricultural projection, and water management strategy developed over decades assumes that the Mississippi will continue flowing toward the Gulf. If that assumption has failed, then countless other predictions about North America's future may also require reconsideration, revealing just how dependent an entire continent has always been on one moving river. As months turn into years, the absence of a flowing Mississippi would begin rewriting more than the environment. It would reshape the way Americans live, build, trade, and even think about the geography of their country. Entire generations have grown up believing that rivers are permanent features of the landscape. In reality, civilization depends not simply on the existence of water, but on a water that moves. Once that motion disappears, every long-term plan built around the river starts losing its foundation. Cities along the Mississippi would face difficult decisions that once seemed unimaginable. Communities that had existed for centuries because of access to river transportation would no longer possess the advantage that originally made them successful. Ports that once operated around the clock become vast collections of idle cranes, silent terminals, and empty docks. Warehouses designed to handle millions of tons of cargo every year begin serving entirely different purposes, while shipping companies relocate investments toward coastal ports and rail hubs capable of absorbing at least part of the lost trade. Some cities manage to adapt. Others struggle with declining employment as industries dependent on river logistics gradually relocate. Manufacturing plants built specifically to receive raw materials by barge calculate that trucking or rail transportation will permanently increase production costs. New investments begin flowing elsewhere, altering economic growth patterns across entire regions of the country. At the same time, engineers launch one of the largest infrastructure programs in American history. Massive pipelines are proposed to move freshwater between regions. New reservoirs are excavated far from the Mississippi Basin. Rail corridors are expanded to replace missing freight capacity. High-capacity pumping stations attempt to redistribute water from remaining freshwater sources toward population centers that once relied almost entirely on the river. Every project requires years of construction and hundreds of billions of dollars, yet none can truly recreate what nature provided without interruption for thousands of years. Even weather forecasts begin changing. The Mississippi Valley has always acted as a natural corridor connecting cold Canadian air with warm, humid air from the Gulf of Mexico. Meteorologists continue studying how a stagnant river influences local humidity, surface temperatures, and atmospheric circulation. While the river itself does not control continental weather, removing such an enormous source of moving freshwater introduces subtle changes that gradually appear in long-term climate observations. Certain regions experience slightly different seasonal moisture patterns. Others see changing fog frequency or altered local temperature extremes near the river corridor. The landscape itself starts revealing signs of a forgotten river. Vegetation slowly advances toward former shorelines. Young trees begin growing on exposed sandbars that once disappeared beneath seasonal currents. Abandoned navigation channels transform into shallow wetlands or isolated lakes. Sections of the river that had remained deep for centuries become fragmented into disconnected pools, separated by broad mudflats and expanding islands. From the air, the Mississippi no longer resembles the powerful artery recognized on every map. Instead, it appears increasingly like a chain of disconnected water bodies stretching across the center of the continent. Then comes one of the most unexpected discoveries. Archaeologists suddenly gain access to places that had remained underwater for hundreds or even thousands of years. Historic steamboat wrecks emerge from receding channels. Indigenous settlements buried beneath layers of river sediment become accessible for the first time. Bridges built during the 19th century, long forgotten beneath shifting currents, begin appearing as water levels stabilize and sediments are removed through excavation. Every month uncovers new fragments of North American history that had remained hidden beneath the moving river. Yet every remarkable discovery carries an unsettling reminder. Those artifacts are only visible because one of Earth's great natural systems has ceased functioning. The same event exposing forgotten history continues destroying modern infrastructure, freshwater ecosystems, and coastal landscapes at an accelerating pace. Scientists monitoring the Gulf calculate that shrinking freshwater input has permanently altered ocean chemistry near the river's mouth. Inland researchers document ecosystems adapting into forms that have not existed for recorded human history. And eventually, one conclusion becomes impossible to avoid. If the Mississippi River never flows again, the United States would not simply recover from a disaster. It would become a fundamentally different country, shaped by new trade routes, new cities, new coastlines, and a landscape forever marked by the absence of the river that once defined the center of a continent. Looking back at every stage of this scenario, one fact becomes impossible to ignore. The Mississippi River is often described as a waterway, but in reality, it functions more like a living circulatory system. It moves water, sediment, nutrients, energy, commerce, wildlife, and people across nearly half of the continental United States. Remove that movement, and the effects spread through every connected system with surprising speed. The disaster is not caused by the disappearance of water alone. It is caused by the disappearance of motion. That distinction changes everything. During the first days, the crisis appears to be one of transportation. Barges stop moving, ports fall silent, and supply chains begin slowing. Weeks later, drinking water systems come under pressure as salt water advances inland, and stagnant water becomes increasingly difficult to treat. Within months, ecosystems begin collapsing, industries reduce production, wetlands deteriorate, and agriculture faces mounting logistical challenges. Years later, the country itself begins adapting to an entirely new geographic reality. None of those stages exist independently. Each one triggers the next, forming a chain reaction that grows more difficult to interrupt over time. This is exactly why hydrologists, engineers, ecologists, and emergency planners devote enormous attention to maintaining the health of major river systems. They understand that rivers are not isolated features on a map. They are dynamic networks connecting thousands of separate processes that depend on one another every hour of every day. Even today, scientists continue studying how changes in rainfall, drought frequency, sediment transport, land use, and climate may influence the future behavior of the Mississippi. Although a complete halt in flow remains an extraordinarily unrealistic event under natural conditions, smaller disruptions already provide valuable lessons. Historic droughts have exposed normally submerged riverbeds, reduced navigation capacity, allowed saltwater to move farther inland, and forced difficult decisions about water management. Those real events demonstrate how sensitive modern infrastructure can be to changes in river conditions that are far less extreme than the scenario imagined here. They also reveal how quickly consequences spread beyond the immediate river corridor. A drought affecting shipping near Memphis eventually influences grain exports in Louisiana, manufacturing in the Midwest, fuel supplies along the East Coast, and food prices in markets thousands of miles away. Every connection reinforces the same conclusion. The Mississippi is not simply serving one region. It quietly supports an entire national system whose complexity often goes unnoticed because it functions so reliably. Perhaps the most remarkable aspect of this thought experiment is that most Americans would never witness the first moments of the disaster directly. Many people live hundreds of miles from the Mississippi and rarely think about it at all. Yet grocery shelves, fuel stations, factories, power grids, export terminals, and water treatment plants remain connected through invisible networks that ultimately depend on the river's continuous movement. The greatest danger would therefore not be what people could immediately see along the shoreline. It would be the gradual realization that everyday life across a continent had been built around one assumption that no one seriously questioned: that tomorrow, just like yesterday, the Mississippi River would keep flowing toward the Gulf of Mexico. Once that certainty disappears, every system built upon it must be reconsidered, revealing that one of the most powerful forces shaping modern civilization has never been the river itself, but the constant motion that people quietly assumed would never stop. Perhaps the most fascinating part of this entire scenario is that it highlights something humans rarely notice. Civilization tends to celebrate massive skyscrapers, highways, airports, and technological breakthroughs, yet the stability of those achievements often depends on natural systems that receive very little attention. The Mississippi River has spent thousands of years quietly performing work that would be impossible to replace through engineering alone. It carries hundreds of millions of tons of sediment every year, replenishing wetlands that protect coastal communities from hurricanes. It supports one of the largest freshwater drainage basins on Earth, collecting water from 31 U.S. states and 2 Canadian provinces before releasing it into the Gulf of Mexico. It provides habitat for hundreds of species of fish, mammals, reptiles, amphibians, and birds. Millions of migratory birds rely on the Mississippi Flyway during seasonal journeys that stretch from northern Canada to South America. Every autumn and every spring, countless birds follow the river corridor as though it were an invisible highway across the continent. If the river stopped flowing permanently, many of those migration patterns would eventually change. Some species might successfully adapt by finding alternative routes. Others could experience declining populations as wetlands disappear and food sources become less reliable. The effects would unfold gradually over decades, making them difficult to notice from one season to the next, yet unmistakable when viewed across generations. The same slow transformation would affect countless other forms of life. Freshwater mussels, among the most endangered animal groups in North America, depend upon healthy river systems for survival. Native fish evolved to spawn in flowing currents rather than stagnant pools. Riverbank forests developed alongside predictable flood cycles that shaped their composition for centuries. Every species represents another thread woven into an ecological network that appears remarkably stable until one critical component is removed. This thought experiment ultimately reveals an important lesson that extends far beyond the Mississippi itself. Similar relationships exist around the world. The Nile supports northeastern Africa. The Amazon regulates enormous portions of South America's freshwater and climate systems. The Yangtze, Mekong, Danube, Rhine, and countless other rivers sustain hundreds of millions of people through agriculture, transportation, drinking water, and industry. Although each river is unique, they all share one essential characteristic. Their value lies not only in the water they contain, but in the continuous movement that connects landscapes, ecosystems, and human societies. Without that movement, rivers gradually become something entirely different. They stop acting as arteries and begin behaving like isolated lakes linked by shallow channels, incapable of performing the functions upon which civilizations have depended for thousands of years. Fortunately, based on current scientific understanding, a complete and permanent halt of the Mississippi River remains an extremely unrealistic scenario. Gravity continuously pulls water toward the Gulf of Mexico, while rainfall, snowmelt, tributaries, and groundwater recharge the basin throughout the year. Even severe droughts reduce flow rather than eliminating it entirely. Yet, imagining the impossible serves a valuable purpose. It reveals how interconnected modern civilization has become with natural systems that often escape public attention. Every shipment arriving at a port, every field producing grain, every treatment plant delivering drinking water, and every wetland buffering storm surges forms part of a chain that ultimately traces back to a river still flowing as it has for thousands of years. It is easy to assume that such systems will always remain unchanged because they have operated reliably throughout modern history. But understanding their importance begins with recognizing how profoundly life would change if even one of them suddenly stopped doing what it has always done. The Mississippi's greatest contribution has never been simply existing. Its greatest contribution has always been continuing to flow.